there. Now the next thing we are going to discuss is colored compounds. Okay, why do transition metals form colored compounds? लेकिन ये discuss करने के लिए ना we have to first learn a lot of things about transition metals. And the first thing we're going to talk about is there's a thing called complex ions, and we will talk about complex ions first. ठीक है? And let me write the definition of what a complex ion is. So it's an ion formed when a central metal ion so a central metal ion datively or forms coordinate bonds so it forms coordinate bonds with ligands. Okay, now this is the definition. I'm going to explain this definition in a while. Uh, First thing is what's a dative coordinate or a coordinate bond? That's a bond where both electrons they come from the same substance. Another thing that needs to be understood is what's a ligand. Okay, first I'm going to write the definition of what a ligand is. Now ligands they are species that do this. They're species which have lone pairs. So they have their lone pairs and can donate a pair of electron or can donate a lone pair, a pair of electrons to form coordinate bonds with metal ions. Coordinate bonds with metal ions. Now, both things, okay, complex ion and ligands, we're going to talk about them in a lot more detail. I'm going to draw a diagram first, and I'm going to explain what happens when the diagram is going to help us explain what's a complex ion and what's a ligand. Now, when you have salt, for example, you have copper sulfate, and it is solid, and you mix it in water and becomes aqueous. Uh, salt salts they usually dissociate and they ionize. Copper 2 plus aqueous ions are formed. Similarly, SO4 2 minus aqueous ions are formed. Dissociate means that that the ions they break away from each other. Usually, what happens is, ठीक है, so usually what happens is that you have these oppositely charged ions. Uh, Copper is +2, so there's +2. Sulfate is -2, and they're all attracting each other very very strongly. What you do is that you take water. Let's say there's a beaker of water, and you put the crystals in that water, and you stir vigorously. When you stir them, the ions are going to dissociate. All these ions, they're going to dissociate and they're going to separate and they're going to scatter in the water. So, for example, this +2 over here, it's going to dissociate and it's going to mix with water. This -2 is going to break off and it would also mix in water. And so on the entire salt crystal is going to dissociate eventually, and the ions are just going to scatter in the water. So you have these scattered ions in solution that are just roaming around and they've been mixed in solution. And the next thing is the reason why the ions don't form the crystal back again is because you have thousands of water molecules that are completely surrounding them and they won't be able to meet them. It's assuming it's a dilute solution. If it's a very concentrated solution or a saturated solution, then these ions can get together and crystallization can happen and the crystal would reform. But if it's a very, very dilute solution and there are lots of water molecules, the water molecules would not allow the ions to sort of meet each other and they would cancel out the force of attraction. I mean, this +2 would be attracted to the -2, but the force of attraction gets diminished because there's so many water molecules in the way. Now, this is the idea that whenever you have a salt, we're focusing on salts that involve transition metals because we're studying transition metals. So whenever you have a salt that is made of a transition metal ion, the ions they mix in water. Now the thing is that they're not just roaming around in water. What actually happens is, now imagine a copper 2 plus ion, and this copper 2 plus ion is roaming around, it's mixed in water, it's floating around in solution. So imagine copper ions have these six sides. There's an x-axis, a y-axis, and a z-axis. And what's going to happen is this copper ion is roaming around in a solution that's made up of mostly water. Now, these water molecules are going to be your ligands. The reason they're going to be your ligands is that water is a highly polar molecule. So if you look at water, water has two bonds. It's a bent molecule, and it has two lone pairs which have a very strong partial negative charge. So there's a partial negative charge, and it's a highly polar molecule. The hydrogen is partial positive, oxygen is highly electronegative. So what's going to happen is that this molecule over here, okay, let's pick this molecule, and it's imagine that this molecule is floating around. This molecule is going to go and it's going to get attracted to the copper ions. The negative side over here is going to get attracted to the it's going to get attracted to the positive ion over here, the copper ion over here in the center. And it's going to start surrounding. There would be lots of water molecules, and the water molecules are going to come in and they're going to start sticking to the copper ions because the copper ions are positively charged. So here you can see another lone pair coming in, and that's getting attracted to the copper ions. So from all sides, you have these water molecules that are coming in and completely surrounding the or getting attracted to the copper ions. Okay, so from all sides, these water molecules are coming in and they're getting attracted to the copper ions. And this now, so the copper ion, the one that was pictured over here, that is not a very good representation. What actually happens is that copper ions are not just only scattered in water, the water molecules are actually completely sticking to the copper ions. And and this entire thing is known as your complex ion. It's written as the way it's written is Cu. There's six water molecules that are attached to it, and the overall thing is going to have a charge of 2 plus. The reason the overall ion is going to have a charge of 2 plus is because water is neutral. So you have water molecules which are completely neutral. And just one second. So you have your water molecules which are completely neutral, and you have your copper ions which have a charge of 2 plus. So the overall charge on this thing is going to be 2 plus. Remember, when different things combine, then they're not going to have an individual charge because copper 2 plus, it's going to get electrons from different sides. So this 2 plus would get delocalized over the entire structure. Okay, so the overall charge is going to be 2 plus because water was neutral in the first place. So I'm going to draw brackets, exactly what you do with the ions around the structure. And this entire thing is going to have a charge of 2 plus, and I'm going to rub off this charge on copper 2 plus now. Okay, so the entire structure is going to overall charge. Now there's going to be an overall charge, no individual charges would exist. So this is known as a complex ion. And it's written in square brackets. Always complex ions are written in square brackets. Uh, so it's copper with six water molecules. The overall charge is 2 plus. And this is a complex ion, and this thing is known as your ligand. These water molecules are your ligands. So let me circle them. Okay, so these are your ligands that we talked about, that we defined. So there's species that have lone pairs, and they can bring in their lone pairs, and those lone pairs can stick to the metal ions. So species with lone pairs that can donate a pair of electrons to form coordinate bonds with the metal ion. And a complex ion is it's an ion formed when a central metal ion datively bonds or coordinately bonds with ligands. I said now the thing is that there are all sorts of ligands and all sorts of complex ions. This one specifically, we're going to do a few complex ions, which are in your A level syllabus, specifically complex ions related to copper and complex ions related to cobalt. Their colors and their shapes and the way you need to learn how to draw them as well. You must remember their formulas as well. Now, this one is your blue, it's a blue colored complex. So you must remember that this is blue in color, uh, which is why it's whenever you must have read that copper sulfate is blue in color. It's not copper sulfate that's blue in color. When you mix copper sulfate in water, this particular complex ion is formed. This complex ion is the one that's actually blue in color. Sulfate has nothing to do with the colors of the compound. And we're not going to talk about sulfate over here, what it's doing. We're just focusing on what copper ion is doing in the solution, okay? Because we are studying transition metals right now. As so like this, uh, the names of the complex ions, you must know the shape as well. This one is an octahedral complex. So this specific shape is your octahedral complex. Uh, Usually what happens is whenever something makes 6 bonds, the shape is octahedral. Like one ligand is attached on the top, one at the bottom, one right, left, front, back. So there are 6 sides to copper and 6 ligands are attached. Now the thing with shapes is that it all depends on the relative ratio of the ligand and the metal ion. The shape is dependent on that. How many ligands get attached? So that's the question. Now, in your case, you have to pretty much remember how many ligands get attached in a particular complex. But remember this. Uh, this thing, the answer to this is that it depends on the relative size of metal ion and the ligand. What that basically means is that you could have a huge metal ion, like a big metal ion in the center, and the ligands that are getting attached. So the thing is that the ligand could be very small in size. So if it's very small in size, you could have lots of ligands that can get attached to it. Three-dimensional space की requirement है, ठीक है? So you could have many ligands that could come in, bring their lone pairs, and they can sort of get attached to the central metal line. But vice versa, so there's this metal line in the middle and lots of ligands coming in from the surrounding three-dimensional space. Now, vice versa, what if the central metal line is very small in size and the ligand is actually huge in size? Now the problem would be you can't really have many ligands surrounding it because you're going to run out of space. So so the relative size of the ions. So this is one example that ligands bring in their lone pairs and the positive ion metal ion is in the middle. But you can't have a lot of ligands or a lot of dative bonds being formed in this particular case. इस केस में बहुत ज्यादा बन रहे थे, इस केस में बहुत कम बनेंगे. अच्छा, so based on this, we can have a general idea, and that is that for octahedral complexes, we can have a general idea that smaller ligands usually form octahedral complexes. Now the question is, how do you figure out which one is a smaller ligand? What you can simply do is you can check MR. Now the MR is going to give you an idea of whether the ligand is small or big. So for example, you have OH minus one, you have H2O, You have NH3. These are all ligands. They all have lone pairs. So they all have lone pairs, and these are considered small ligands. Small ligands, you can fit a lot of them around a metal line. A lot of them are going to go and stick around the metal line. Uh, इनकी MR भी check कर लो. The MR of these substances, this is 17, this is 18, I think, and this is also 17. So the MR is less as well. But on the other hand, if you have a bigger ligand, now bigger ligands uh, like Cl minus 1. So Cl minus 1 is a bigger ligand. The check the MR of Cl. It's the AR of Cl is 35.5, 35 or 37. So it has more shells. So it's a much bigger ion because Cl is has 17 electrons, so that it has 3 shells. So it's relatively the size of the Cl ion is going to be much bigger. Now bigger ligands like Cl minus 1 usually form octahedral complexes. So they usually form octahedral complexes. You can't fit a lot of them around a metal ion. So one example is, and this is another example, and you must remember the color of this complex. And that example is Cu with Cl. For example, if you add copper ions and in a solution of concentrated HCl, so there would be Cl minus 1 ions that would be roaming around. The Cl minus 1 ions are going to get attracted to the lone pairs are going to get attracted to the copper 2 plus. So from all sides in the three-dimensional space, you would have Cl minus 1 ions that would be getting attracted to the copper 2 plus. So from all sides, you have Cl minus 1 coming in and they're getting attracted to the copper 2 plus, and this is going to be written as there's one copper and there are 4 Cls. The overall charge is going to be, if you add up all the charges, this is 2 plus. The other ones are all minus 1, minus 1, minus 1, and minus 1. So the net charge on this complex, remember you have to write complex ions in square brackets. So there's one copper with 4 Cls, and the net charge is uh, 2 minus. Okay, that would be the net charge. And you're not going to write when you draw this complex ion, you're not going to write these individual charges. So I'm going to rub those individual charges off. They need to be removed. Now the entire complex ion is going to have just one single charge, which is which is going to be 2 minus. Okay, so this is your CuCl4 2 minus complex, and it's yellow in color. One thing that I wrote incorrectly was that I should have used the word octahedral. Octahedral to पिछला था. This shape is tetrahedral. So let me correct that as well. It's they usually form tetrahedral complexes, not octahedral complexes. Only 4 Cl ions are going to get attached. And another thing about this is that instead of actually looking yellow, it actually appears, most of the time, it appears green in color. The reason it appears green is okay, when you add these Cl ligands, concentrated HCl, for example, there's going to be water present. So there are chances that this first complex might also be formed. So in the solution, you would have a blue colored complex because of the presence of water. And because of the presence of Cl ions, there's going to be this yellow colored complex. So blue and yellow combine to form and they would appear green. TK, you must know that blue and yellow, if you mix them, they look green. So most of the time, it doesn't actually look yellow, it actually looks green in color. As a similarly, I'm going to draw a few more complexes. TK, the ones whose colors you should be aware of. Okay, so this is the next one. It's copper 2 plus with its 6 sides. Okay, this bond is coming out of the page. I say, anyways, you have this copper ion, and it could be surrounded by ammonia. So you can have NH3 molecules. If you add NH3, then you can have all these NH3 molecules coming in. Bringing the lone pairs, the lone pair on N is going to be attracted to the copper ion. And again, this entire thing, this would be written as Cu. There would be 6 NH3s. The overall charge is going to be 2 plus because NH3 doesn't have a charge. So the overall charge on this entire thing is, it's going to be 2 plus. And this appears deep blue in color. Now, also remember one thing, that the bonds that are formed over here, the dative bonds over here, they're not very strong. Now, what happens is, usually, most of the time, these bonds over here are not very strong. When you add NH3, a lot of times you're adding aqueous NH3. So there would be water molecules around. So let's imagine there would be a few water molecules. Let's imagine there would be a few water molecules roaming around. So there's not going to be just one ligand in the solution. There could be many ligands. There could be many substances. So for example, aqueous ammonia, NH3 aqueous means there's going to be water present as well. So these bonds can easily break as well. I mean, this NH3 molecule can drift away as well. It's not necessarily that it's permanently bonded to it. Uh, the copper ions, remember, I told you about transition metals, that transition metals are not like non-metals. They like to gain electrons, but they don't like to, they don't like to gain electrons. They have a weak attraction for electrons. The thing about transition metals was that we discussed earlier as well, because they have more protons. So they don't like to lose electrons, but they have a weak attraction for electrons. So it's a weak attraction for electrons. It's not a very strong attraction for electrons. It's not like non-metals. Non-metals के case में क्या होता है? The electrons are permanently gained by non-metals. Over here, this ion is going to be weakly attracting these electrons, not very strongly. So this bond can kind of break away, and the NH3 can drift off. And in its place, water molecules can come in. So it's not always the case that all the ligands are exactly the same. Most of the time, remember that water is going to play a role, because most of the solutions are actually the medium that's used is water. Now, if this happens, and there's one water molecule over here, the way you're going to write this complex ion is going to be that it's Cu with one water molecule, and there are 5 NH3 molecules. Now, in total, you still have 6 ligands attached. Okay, so it's this is how you're going to write this molecule. And this is the ion. So remember this, the ligands are not permanently attached, and they can be replaced or exchanged. We're going to study ligand exchange in detail, uh, probably in the next class. But remember, these ligands are not there and they're not permanently attached. The Cl could also break off. The water molecules over here in the first ligand that we drew, they can also be replaced by any other ligand. Okay, so we're going to discuss the last copper complex, and that one is the last one. That one is copper hydroxide. So you have this copper 2 plus again, and you have let's quickly draw this. As we have this copper ion, and it's surrounded by water molecules. So all sorts of water molecules attached. But on two sides, there's an OH minus one that's attached. That also has lone pairs. The oxygen has lone pairs. Then you have water molecules and more water molecules. Now this is known as Cu, OH2 twice, and there are four water molecules in the complex. The overall charge in this case is now zero. The overall charge is zero, and because the OH is minus one, and the copper over here is 2 plus. So the overall charge on this complex is going to be, it won't have a charge, and it won't attract anything else because the overall charge is neutral. I said now this thing is going to eventually form a pale blue precipitate, and it would eventually form because it's neutral, like copper with two hydroxides. It becomes completely neutral. Okay, so why would it attract the other water molecules as well? So it eventually ends up forming a pale blue precipitate. I mean, imagine. Let's go back just a step. Imagine you have copper with six water molecules. The reason it's attracting the water molecules is that even if the water molecules come in, the water molecules overall are neutral. So the complex ion has a charge of 2 plus, right? I mean, there's a charge of 2 plus. So even now it can attract other water molecules. The only thing is it doesn't have any room or space left around it. But in this case, imagine the same thing like the water molecules they got replaced. Okay, actually, this wasn't really water. This was OH minus one. So imagine you have six water molecules, and two of the water molecules they got knocked out by OH minus ones. Now OH minus one comes in. Now if copper 2 plus combines with two OH minus one, the overall charge on this complex ion would be zero. If it's zero, then the attraction for these other water molecules and their lone pairs, it's going to diminish. It's going to be lesser because पहले तो copper के ऊपर 2 plus था, but now I mean this entire thing, if you look at these things, their overall charge is zero. So they would stop attracting water molecules, and they're going to end up forming a precipitate, and it's going to be a pale blue precipitate of copper hydroxide only. The attraction or the affinity for water is going to decrease. So basically what you need to know is that this is going to be a pale blue precipitate. Now these colors have to be memorized and the structures have to be memorized, how to make them. Uh, this is deep blue. Actually, this copper with NH3, even with water, is also still deep blue. And there are a few more complexes that you need to remember. There are complexes about cobalt. Now you must remember the cobalt complexes and their colors as well. I said now I'm not going to draw them. They're exactly the same as Cu2 plus. There is hardly any difference. Exactly the same. The only difference is that the colors are different. So for example, there's cobalt with six water molecules, and the overall charge is 2 plus. This is pink in color. Okay, so it's exactly like it's exactly like the first one. So this one is exactly like the first one. Then there's another one with copper and OH twice with four water molecules. Overall charge is neutral. This is a green precipitate. Then you have cobalt with the four Cls. This is blue in color. And then you have cobalt with NH3. And this is brown in color. Okay, so the last one is brown in color. So these complexes, they need to be memorized as well.